I'm Alon Yariv, previously CEO and co-founder at Atero AI. We were recently acquired by Crusoe. I became VP Product Partnerships Innovation and GM of the Israeli site. Longest title I've ever had. And what I wanted to present to you today was something that we have worked extensively during my tenure in Atero, and now we are building within Crusoe, which is building a good way to scale inference beyond a single node. Now, what exactly do I mean by that? In the last few years, we have seen a phenomena happening in front of our eyes. Models became huge. The assets that relate to models became huge. The deployments became huge. I start sounding like Trump. But with those huge deployments, complexities came. Now, the complexities mainly rose from the fact that all of a sudden, you don't have your model running on a single machine, but you have it running on thousands of machines. Those thousands of machines need to manage different sessions of different users. And all of those different users have different LoRa heads. They have different KVCache assets attached to them. They have different chat histories, different assets within RAG systems attached to them. Now, all of those things, compared to the software we had before AI, are about 2 to 3 orders of magnitude larger. So typically, when you would build a user-facing application, a gaming application, a social media app, whatever, the user-specific assets would be a kilobyte, 10 kilobytes. Those are easily fetched from a Redis database locally. Those are easily fetched from an S3 bucket. And latency doesn't really matter too much. But imagine all of a sudden you are building a cursor competitor, and you need to fetch, for a specific user, half a code base, like half the repo of vLLM, for example, if that's what he's working on. So the assets became huge. They became impossible to store locally, or too large to store just locally within the GPU. And you have seen an explosion of different solutions over the last years, last year mostly, that allow you to actually help with that. So in the end, I will show you the slides if you don't know what is KVCache. So KVCache in the world of machine learning means a specific key value cache that sits within the GPU HBM that hosts the previous computations of the attention heads. This allows you, when you're building some AI application, not to recalculate the entire prefill, the entire history, every single query. It has all of the computations already within the cache, and then it just computes the next token. Using KVCache makes your life a lot faster. It's like 10, 20 times faster than computing the entire prefill, but it's also really heavy. So now I want to, well, I'm less of a technologist than anyone here in the room, so you can build those stuff much better than I can. But I like to focus on the use cases and why we're building stuff. So why do I care about KVCache? There are a few use cases that I constantly have in mind when I think about, like, why would you need massive pools of KVCache available for your user base when you're building an AI application? The first use case is also the most predominantly used case in AI currently, which is software development. So in software development, your model, almost for every single request, needs to pull massive chunks of your code base, massive chunk of your previously written data in order to answer a question. Now, the question is tiny. The question can be like, where does this function appear? Or what does this function do? Or how does it interact with other functions in the code base? So the ratio is like a tiny question, huge context, tiny answer. This means that you are constantly pulling massive amounts of data, producing tiny amounts of data, and if you need to recompute all of that, it takes a ton of time. The second use case is customer service. Same phenomena happens here. in order to answer a customer-specific question, you need all of the customer history, all of the products they have been buying from you. You need all of the conversations they have had with representatives before. If you're building an agentic use case, it's like you need to remember all of the history that the agent has gone through. So again, massive context, tiny output. Same thing goes with marketing. You're building like an agency of agents building assets for marketing departments. You need your entire brand history, existing assets in order to answer that specific question. And knowledge databases, so knowledge and search. What you would typically see in these type of use cases in AI is RAG-based applications. RAG-based applications tend to be slow, especially if you need to fetch a lot of data, because they always require recomputation of that data. All of those use cases are, or at least they tend to be, extremely slow in response rate, because you are constantly recomputing stuff that you have already computed. Now, let's say you had like a massive KVCache shared between all of your sessions, all of your users. With a software development application, what you could do is calculate the attention head once for the entire repo, and actually share those assets from a single location to all of the GPUs answering currently customers, ship the specific context relevant for the query to the specific GPU, and then you don't need to compute those tokens. In coding applications, having something like that available to you can reduce the overall latency by about a factor of 10 and increase the throughput by about the same factor. So those are massive improvements. Companies like Poolside have worked extensively on allowing like KVCache swapping within their prefill. You have like articles like cache blend, because there's all sorts of challenges arising from there. But the main thing that companies have resorted to do, and primarily, predominantly open source projects, and us at Tero, they have rethought where do we store the KVCache. So KVCache is in a GPU. GPUs, HBM, are expensive and tiny. Maybe we can extend it to DRAM. So when you're extending your KVCache to DRAM, this is called offloading. So it's essentially using a cheaper resource that you have in a larger amount to store those assets. All sorts of challenges arise from that. You need to transfer the assets in and out of DRAM extremely quickly in order to this actually make any benefit. This is what LM Cache are doing very well. The folks from Dynamo went with a slightly different approach, or at least a slightly different focus. Tyler, actually, if you want to read a little bit about more LM Cache, like they're an extraordinary team. They built an amazing product. But yeah, it's I will go back to those slides because there's some beautiful paradigms that we have seen from the emergence of Kubernetes happening in the same very much way here. NVIDIA in March came out with this announcement on solving the KVCache problem with Dynamo. Now, a lot can be said about Dynamo, but the simplicity of it is that their main focus is doing disaggregated inference. The idea is like, okay, you can host KVCache on another machine, you can compute the prefill there on a cheaper GPU, and then once you need this prefill, you can fetch it to a faster GPU that will actually do the inference. So they are one of the early frameworks that thought about extending beyond a single node the process of doing inference and the process of storing KVCache. The folks in LLMD is a project that came out of Red Hat, heavily supported by the folks in CoreWeave. LLMD have sort of gone after a very Kubernetes-y approach to how you build a deployment of a model. And the main aspect they have improved upon in their project is actually the routing of the user requests. So when you have KVCache-aware routing, you are not going to recompute stuff again if you already have the cache on a specific GPU, which allows them to achieve a significant performance gain. And AI Bricks is offering a full stack integration of both managing KVCache across a plethora of nodes, as well as building the load balancer and the KVCache aware routing. Now, the technicalities are interesting, but what I have seen in this market is mostly a paradigm game. When we had Docker and containerized applications early on, we had two different types of paradigms. We had people that are focusing on the container image and the container runtime, and we had people that are focusing on the actually how you make it into a distributed system. So all of those projects, AI Bricks, LLM Cache, LLMD, etc., those are sort of the equivalent to what Kubernetes was for the world of Docker and containerized applications, for the world of machine learning. And you see the same two approaches as we had with Docker Swarm and with Kubernetes to how you build AI applications. So the folks in LLMD, they look at it as like, segmented nodes with segmented resources, and the atmosphere behind it is like we are building the next Kubernetes equivalent. And the folks from LM Cache and AI Bricks, they very much go into the Docker Swarm type of philosophy. Now, as we remember from the days of Kubernetes, it was extremely difficult to deploy Docker Swarm and actually manage it and scale it. Like those are the challenges that you don't want when you're building an open source project, because it makes it extremely difficult to deploy. That's kind of what's going on with the companies that went into that direction. But it actually, at least in my personal belief, it's the better approach to how you manage those type of applications, because you get an integrated stack that allows you for better performance and better utilization. Now, what we build in Atero is actually sort of going in another direction. Like we are building a fully integrated vertical system that allows you to take benefit from writing our own RDMA-based libraries that allow you for significantly better performance than Nixel and competitors alike. We are building our own routing technology. We are integrating our solutions to the runtime and making modifications to vLLM, SGLang, whatever we're using underneath. And because we are not open source yet, it allows us to have it deployed in a predictable environment, on predictable GPU cluster, and take benefit from this fully vertically integrated approach. Now, this is an example of what we can get from actually building the entire stack from the bottom up on our own. And it used to be Atero, now it's Crusoe, a pretty recent change for us to experience. But this is a benchmark that we have run against the other approaches in KVCache compared on a single node performance. Now, why I'm showing you a single node performance versus a fleet? Because this is a testament to how fast we can shift data between DRAM to HBM. Like, we have rewritten communication kernels that allow us to surpass performance of any existing RDMA library, even when we are competing on like a very experienced landscape. Now, the beautiful thing is that our performance gain, let me explain to you what you see here. So we ran Llama 8B on a single node, but multiple different instances of this Llama 8B, and we offloaded the cache to the DRAM of that node. So you have multiple different Llama 8B models running on those 8 nodes. They have their KVCache stored on DRAM, and this KVCache is shared. So if I get a request to deployment number 1 that is like following a session that started on deployment number 2 or 3 of that node, you are actually going to fetch cache that was not attached to that specific session. So you're sort of switching the location, the physical location of a specific session. Now, what you're seeing here is what is the time to first token of such a deployment with some benchmark that mimics the behavior of a chat application. The vLLM bar shows you what happens if you don't have any cache. Like, what's the time to first token if you are recomputing the entire prefill. The bar next to it, and I'm sorry if somebody is colorblind here, the colors are terrible for that. I chose them. Vast is an example of how to fetch it from storage. So Vast came up with this idea of let's not offload to DRAM, but let's offload to a storage on another machine and utilize the RDMA fabric to fetch the context. So as you can see, when the context gets larger, the difference, it does become sensible to move it from storage, but storage is far and the latency is relatively high compared to local machines. That's why it doesn't excel. AI bricks and LM cache, you can see that they produce a large advantage over recomputation, even if like on the same node. And the Atero stack, now Crusoe, offers almost an order of magnitude of improvement, even if it is not localized. Now, the same thing goes, oh, wait. I did a GPT mistake, but it's really 11 times faster. The graph is just, I did it in Figma, so I'm not really good at that. So this experiment showcases a comparison between recomputing what we have in KVCache versus fetching it from a remote machine. So this time, we are not fetching from local DRAM, but we have the KVCache asset on in another node in DRAM, and we fetch it over our own Atero which is our Rust-built RDMA library. The geniuses that built it are sitting there. I didn't help. But anyways, this allows you to fetch it from a remote machine and still gain an order of magnitude of performance. Now, imagine what happens if you scale it to thousands of machines. You're effectively increasing the KVCache size for a specific model by 3 orders of magnitude, which means you can put an entire encyclopedia in cache. You can put an entire multiple different repos in cache available for your models. You can put your entire enterprise search in cache. And we have seen real-world use cases where this allows you for, especially in cases where they're predominantly input tokens based, it allows you to save an order of magnitude in cost, an order of magnitude in computation. This is why I'm super excited about this direction, and I think there is a lot of good work happening in the open source world. If you want the data about the open source libraries, I share this presentation with everybody. Feel free to take a look at it, because I don't think I did justice to the text there. And yeah, it's a pleasure being here. If you have any questions, I will be happy to answer. If those are things I cannot answer, I might ask Omer to answer. And that's it.